Welcome to everybody. Good morning, good afternoon, good evening, wherever you are. We are here, myself, Mauro, and Tino. Let me check if I really have control of the presentation. Seems not really.
It's now controlling.
I'm not controlling, but as a matter of fact, I cannot control. Okay, so welcome to this webinar. As said, myself, sales director of GMI, the company who's offering this free of charge webinar, and we have here together. I'm here together with Tino. Okay, I'm our functional safety director. Together is not really the proper wording because I'm in Italy while Tino is connected from Germany. Thanks for being here. So this is one of the many webinars we are delivering at the moment in this COVID period. As Tino was saying, the topic today is relevant to some specific aspect which we normally face while selecting components of a SIF or designing a SIF itself, and it has to do with reaching the safe state of a SIF by de-energizing or activating. Before to enter into the detail of the webinar, I would like to give a short introduction of the company. Let me check. Okay, yes, the short introduction of the company. GMI International is a company who design field equipment, field interface for equipment. Our equipment has to do with safety, both case functional safety and intrinsic safety, and our products are mainly in almost all packages, all automation packages like DCS, CSD, fire and gas, BMS, and so on and so on. In most often the industrial sectors like oil and gas, chemical, petrochemical. We have 40 years experience in designing these products. We are established in Italy, where we have our production side, our research and development. We do everything from here in Italy. But of course, we are a global player with presence worldwide. We will see later. As said, dealing with safety, one of the most important things is quality. That's why we are using the possibility through a certificate issued by third party to develop seal-free equipment. Here it is an overview of our product. We have barrier, safety relays, isolator, power supplies, multiplexer to be located in the field until zone 1, for example. Our product can be mainly relays, isolator, and barrier can be installed in beam rail, power bus, or even we have developed termination boards to connect, customized termination board to connect most of the DCS and DSD system. We have arc multiplexer, surge protector, and so on. All these equipment are either certified for functional safety up to C3 level, or they are intrinsic safe. We have finally also our functional safety training and service department. Tino is our director. We provide in the market training and support like consultancies. We will see later in a few words this subject. As said, we are present worldwide. So we are located in Italy as a headquarters, but we have a subsidiary worldwide. We have partner, either they are distributors or agent, and we have offices worldwide. Normally in a non-COVID time, we deliver something like 20 training worldwide about functional safety. We are connected with the TUV, and our training can grant, when the test is succeeded, to get the aimed certificate, as which certificate the person as a functional safety engineer. But again, Tino will say something about that. Okay, presence worldwide, and worldwide we have many customers. Of course, we deal with many type of customer, mainly with system vendors directly or through system integrator. We are dealing with EPCs. We have connection and agreement, technical commercial agreement with OEM. And of course, we have connection with many end users. This is just a short list, which I'm not going to comment in detail. Why? Also because I want to leave the time to Tino to go in detail of the topic of today's. So Tino, you can take back the control, and you can start your presentation. Just one thing to add, to mention, we received, during the registration stage, we received some questions, and we have collected them, and we have a final step of this presentation, of this webinar, where we will answer to this question. Of course, in the meantime, you still have chance to raise questions through the chat. While Tino is talking, I will monitor that, and I will stop him in case of a question is raised, which is worth to be replied during the presentation. Otherwise, we will do later at the end. So, Tino, thank you, and please.
Thank you, Mauro. Thank you, Mauro, and also GMI for giving us the opportunity for doing another webinar on the topic of functional safety. As I said before in the introduction, very briefly, today's topic is something specific, which when we selected that title, some people were giving comments and saying, you really want to discuss something simple. And I said, it is simple if you understand it, which is always true. If you have a basic understanding of those concepts, then it's not complex and it's not an issue. But we come across many, let's say, generic questions from people around in the industry that are always related to the specific ones here. And that's why we decided in GMI to do de-energized versus energized. As Mauro was saying, we have already pre-registered some questions, I think like 4 or 5, which already prepared the answers for, which we're going to see at the end. Now, if you do have some new questions as we are speaking now, you can fill them in the Q&A box. So the Q&A will be monitored by Mauro. And if there is something that I need to, or I cannot answer on time, or as we speak, I will try to do so. Okay, so let's start with some fundamental basic principles. Is that your safety instrumented function shall be specified in a document, which is another webinar of GMI, which is called Safety Requirement Specifications. That means one detailed loop description, one safety instrumented function description shall have specific descriptions and specific definitions that people will know how to build the system, how to maintain the system, and how to operate the system. And of course, it must be expressed in such a way that anyone reading this will know exactly what this safety loop is trying to achieve. In other words, it shall be describing things like, for instance, what hazard do we try to protect us from? What is my sensing element? What is my logic needs to be carried out? But one specific item out of the 29, which is here the second last bullet, out of the 29 items in the chapter 10 from the normative part 1 of the 6.15.11, there are 29 requests to be described in terms of definitions. And one of them is called requirements relating to energize or de-energize to trip for every single SIF. So it doesn't matter how many safety instrumented functions you may have in the field, every single one of them shall describe if this one is a de-energized principle or an energized principle. And for the sake of the presentation here today, I have abbreviated, and there are many different abbreviations. Even the internal documentation from GMI is also using a slightly different, let's say, abbreviation than the one that I'm proposing here. But de-energize to trip, I call this here DET. So de-energize to trip is what I have abbreviated to. Majority of all the safety loops in the field, it's very common to find the majority all as a de-energize to trip functionality. And there is a main reason for that. The main reason is, from the principal point of view, we call this the fail-safe or fail-to-safety principle. So de-energize to trip is often also referred in some documents the idle current principle. That means when you take away the power, you take away the current, there should be somewhere energy in that final device, which is typically like a spring return actuator, that when you take the instrument there away and you have a fail to close valve, the valve will close. That is the principle. From a design point of view of your safety PLC with your interfaces like interposing relays, it's typically that the digital output module from the safety PLC will remove the power on the channel, and the channel will be required to shut down the final element. But there can be many different interfaces in between, and that is why we will make here some specific examples, which hopefully will be clear at the end. So when we say de-energize, taking away the energy, of course you still need something enabled to close. For instance, when you are having a, let's say, when you have a actuator working on instrument air, when you take the instrument air away, you will have to be able to vent the instrument air and able to make movement for the spring to close the actuator. That's a very simple example. Remove the power is typically known as removing electrical signals, removing pneumatic signals, or even removing hydraulic signals. But the basic principle remains the same. We want to go to a safe state, and the safe state of your safety instrumented function is designed as such that the safe state needs to be able to bring the process into a condition where the hazard can no longer evaluate into becoming a risk. Common examples of subsystems that transitions a system into a safe state are, of course, the ESD, or the emergency shutdown system, as most likely most of you will know, or maybe some trip systems. I'll start here with an example, and the example itself is with one single loop from end to end, so from the sensor all the way to the final element. And I make here a very simple proposal. We're going to assume that that measurement over here on the sensor on this transmitter needs to measure a certain pressure. And when the pressure is reaching a certain trip point, the logic controller over here in the middle has to make sure that it can close that particular valve. That is the principle which we say over here. So you can see we call this here subsystems 1, 2, 3, 4, 5, and 6. And all of them may have a different meaning on how to achieve this safe position of this final element. The final element is here a mechanical valve. You see here an actuator with a positioner on top. That means you have to remove here, through this solenoid, you will have to remove here this instrument there. Of course, it will not be that solenoid, it will be a different type because it is not a three-way. The picture is from a very simple solenoid, but it should be a three-way solenoid that you can actually vent the instrument air out of this actuator. It can only do so when you remove the power here on this coil of this solenoid. Of course, this can only happen when the interposing relay will actually follow the right command from the safety PLC. In other words, if that relay, you have to check what type of contacts are you using, because typically here, this would be, in this case here, a normally open contact. That means when you remove the signal from the output module to the relay should be able to remove the power on the coil, and that should be removing the air in that actuator. But everything has to work together. Same here with the safety PLC, even the same here on the front. So when you have your smart or hard transmitter, of course it must be accurate, it must be it must be calibrated correctly. Your trip point must be programmed correctly here in your safety PLC. And if you are using a barrier over here in the middle, well, that also needs to fulfill the function in order to give the right signal to that interlock. So in principle, if everything is working well, oops, if everything is working well, then from sensor to final element, that safety function shall be carried out. Now, before we continue, and I just noticed we have the first poll question coming in, and the first poll question is something that I want to read out for you first. The role of the power supply for your instruments and your devices in a de-energized to trip application. And here you have the options. Is a reliability issue for that safety instrument and function. That is the first option you can select. B, it is an availability issue of that safety instrument and function. That means availability, can my safety function be carried out, yes or no? Topic number C, can be both a reliability and an availability issue for that SIF. D, it is irrelevant because we speak about de-energized to trip application. And E, none of the above. That is the poll that I would like Mauro to start now.
Yes, but sorry, Tino, for some reason I have no control on polls.
And I think the reason is I forgot to make you, see, it's always good to have Murphy's Law in here.
Yes, yes.
Can you try now, Mauro? I think I forgot to make you a co-host.
Yes, yes.
That is right. What is the main topic, but I can do this quickly now. It's my mistake. And I see people are answering in the Q&A. I will come back in a minute, but let me first mark. Okay, sorry, Mauro. We were chatting too much before we started. Yes. You are now the co-host. So now you should be able, let me go back. You should be able now to pull the poll question. Apologize for the small delay.
Okay, I am able to launch now.
Very good. So there's only one correct answer possible. It's not a multiple answer potential here. Well, we see the polls are coming in. Mauro, we have
more than 50% at the moment. We just wait a few seconds again, and then we end the poll and we release the results.
Okay.
Okay, I think we can.
Yeah, I think it's
polling.
Getting very quiet.
And share results.
Okay.
Here are the results. Can you see that?
Yes, I can see the results. Probably the rest can also see them. As you can see here, the majority of you took answer C, can be both a reliability and a availability issue for that SIF. I have to say I'm positively surprised that the majority is thinking correctly, because there are very often people thinking that the role of the power supply in a de-energized to trip has no issue to the availability of that system, which is of course not correct. That means we will have later on, I got a few slides that I prepared for that, and we will talk about over voltage, under voltage, all of that. But the role of the power supply itself is again another webinar that GMI has launched a couple of weeks ago, which is also available on the YouTube channel of GMI, like all the other webinars. Like we only have here 12%, which is saying it is irrelevant, that's answer D, it is irrelevant for a de-energized to trip application. Unfortunately, that is not correct, okay? And a reliability issue only, well, it's also an availability, as I will show you later. So none of the above was a very small percentage, but I'm happy to say that the majority has taken here answer C, which is in my, let's say, understanding to the standard, also to the practical experience, is the only correct answer. Okay, so let me just close this and continue. Right. Let's first start with in normal conditions. That means in normal conditions, everything is working normal. That means the pressure we were trying to measure is inside the working range. So there is no reason to stop or to trip that functionality. And the system means the complete system, as you see here, the picture on the right-hand top is maybe Mauro changing the mouse, no? Are you playing around with the mouse, Mauro?
Not now, sorry, I was.
All of a sudden the cursor was like going
mistake.
to the opposite direction. It's okay. It's because I was giving you maybe too much control, but it doesn't matter, sorry. So the loop over here on the right top corner, that was the one we showed before. Assume that there is no internal failure. It means every device is working as per design and there are no internal failures in that system. So the subsystems are all failure free and are working per requirements. That would be the normal process conditions. Now, if we talk about the power supply, the subsystem power supply, like for instance here for the transmitter, the barrier, the relay, even for the logic solver, even for the coil of the solenoid, well, the subsystem power supply needs, of course, to be reliable. In other words, it needs to be accurate, because there will be a percentage that it needs to be accurate, like 1 or 2% accuracy on a power supply is a common thing to find. Of course, we are also aware that under voltage, some of the equipment may not work as it should be. So when you have a under voltage problem, like a voltage drop, or maybe you have on the power supply itself, it is losing the accuracy. Instead of 24 volt, you may only have 20 volt or whatever. Some devices, subsystem devices, will start to fail upon a certain range of an under voltage. An over voltage, that's also what we are very scared of. An over voltage, we don't want to have a problem in our devices, especially in our instruments in the field, caused by an over voltage. And the reason why I'm explaining it this way is I'm just recalling a practical incident of an offshore platform in Norway, where they could not shut down their safety system loops for the simple reason they had an over voltage problem and the devices in the field were damaged. And some of the critical safety instrumented function or loops did not actually reach the safe state and could not reach the safe state anymore because of an over voltage problem, which was not covered by a overcurrent or an over voltage protection units, like for instance a just trying to find the right name now, fuse. I was thinking about another language for the moment, sorry. So under voltage and over voltage are two items that needs to be diagnostic protected according to the IEC 61508. And the IEC 61508 is actually the leading standard for all those manufacturers who are developing such type of devices to be used for safety. Also, latch up or high inrush current is also something that needs to be avoided on such type of field power supplies or instrument power supplies against overcurrent. And that's all the reference coming from the 61508. Availability, of course, even when I recall my first instrument year, which was in 1987, 1988, even there we were using redundant, classical, traditional power supplies. Nothing to do with anything with 61508 because the standard did not exist in 87. But even then, we were using two power supplies. We were making the normal diode bridge in the back, and we were building a kind of a bridge enabled to give ourselves an opportunity for some redundancy. That means availability of power is made by redundancy. And of course, the more modern systems then later on, they were using with load sharing, hot swappable backups, etc., etc. And again, if you want to hear a little bit more about power supply specific, what makes it now a normal power supply versus a still called compatible, suitable power supply, what is now the difference? It will be all to do with here, this reliability, which needs to be diagnosed by the 61508 part number 2. Of course, another thing is the instrument there needs to be available as well. Without the instrument there, well, items will also start to fail, or maybe some items will go to a fail-safe state. Of course, that instrument there needs to be dry, needs to be clean, needs to be accurate, needs to be free from any moisture or any particulates that would be inside the instrument there. So that's all normal items that we try to achieve in our instrumentation. Now, executing the safety function, as I already was explaining it in this example over the safety loop itself, we will now go step per step and we will go through this loop and we will look on how do we now de-energize? What do we need now to go to a de-energized mode? Once the trip point of the pressure transmitter is reached, that means it was recognized by the transmitter, it was led through by the barrier, it was going to the analog input module providing the right interlock logic in your safety PLC, recognizing the trip point. It was powering off the digital output module. The digital output module was powering off the interposing relay. The interposing relay was able to open the contact, open the load to the solenoid. The solenoid was able to remove the air vent of the actuator. And that is still the whole scenario that we want to look to it step by step now. So what I explained just is all here in text. I will save you to read the text because those slides will be sent to you on PDF, if I remember well, by GMI. Plus also, we have this webinar, which we are holding now. We will have it recorded, available free of charge on our YouTube channel for GMI. Let's focus now on de-energize, taking away the energy. And we will focus first here on the safety PLC, together here with the interposing relay. Now, modern safety PLCs will all work with a kind of a diagnostic feedback. I typically joke when I give training classes in the SIG 1508 that turning off the power is very easy. Why? Well, you just cut the wire, you open the switch, you pull the plug, you pull the module. Whatever you do to power down is more or less an easier way than to power up when there is no power available. So simply speaking, to power down, how those diagnostic-based safety PLCs are working, they know they send a signal to their I/O bus to a certain specific channel on the digital output module. They will work with a kind of a feedback channels. And those feedback channels sometimes are also called the watchdog principle. So the watchdog is a kind of a feedback signal. You send something to the field and you try to measure back that the field is receiving what the CPU/IO/DO channel is sending to that field channel. So removing power, there can be multiple independent ways to shut down. And I clearly say independent ways to shut down because we don't want to depend on one way to shut down, because if you have a particular problem on that shutdown channel, you will not be able to remove the power. And I do recall some older safety PLCs that had some issues that the diagnostics were not as they should have been, as complete as they should. And they could actually not remove the power on a digital output module. And in a panic, they actually had to remove the power on the complete module. So it all depends what brand you are using, what systems you are using, but the more modern systems can dedicate, isolate, channel per channel, the power going to the field. Let's focus now on the safety interposing relay. And as we here are working with a webinar which is sponsored here by GMI International, I took the courtesy to take some pictures out of their product manual. Although I'm not a product specialist, I am not actually knowing all the details of the product, but I think everyone listening to this webinar will understand the principle of an interposing relay. So the interposing relay may have multiple contacts, ways to remove the power. That's here an example on the right bottom corner, which is a specific type, which is the 5096 and the 5294S. Both are the S version. You see here on the left, that's a picture of that solenoid coil. And you see here on the right, that's the field power supply, which is actually being cut by two independent different ways here on those contacts. Those are 2 times 2 normally open contacts. Again, if you want to go a lot more in depth about the ways to shut down, etc., there is another webinar available, which is done by some specialists from GMI, which is the real application for relays with line and load monitoring. Now, what I just mentioned, line and load monitoring, when you take a traditional interposing relay, you may not have the, let's say, the diagnostic capacity inside that relay because there is nothing in there to monitor. I mean, a normal, traditional, old-fashioned safety relay is purely a coil and a contact. That means you remove the power of the coil and the contacts are supposed to go open. And in able to make sure they will go open, of course, they will use multiple contacts and multiple coils in series. That means they will go like to open the load to the field with a normally open contact. The relay internal kitchen may have 3 independent contacts in series with each other. So they have 1 out of 3 chance to open those contacts. That means if 2 of them are not working, they still have the 3rd one left. So they will build, let's say, the hardware fault tolerance inside that device in able to achieve the minimum architectural constraints on the tables, table 2 and 3 of the 61508. Now, without going too much in depth, simply speaking, when you look at this picture over here, the left-hand side is actually the functionality of the relay. The right-hand side is purely a functionality to, let's say, diagnose the efficiency of the line, of the contact, of the short circuit, of the earthing problem, etc., etc. And that information can be very crucial in your design of your loops to feed this back to the safety PLC platform. Because some of the safety PLCs, they may not be able to actually handle the load on the length of the cables, on the solenoid coil, in the impedance or the power itself. That means you will have to work with an interface which is called the interposing relay. And we will see later on when we are talking about the opposite topic on the energized to activate. That is where you will see that there are modules then coming in with the line monitoring. And that's specific where this type of modules, which I'm showing you here, let's say this type of interposing relays with diagnostics built in the relay itself, are very crucial for a, let's say, a safety position of your safety loop. I got here, I see that questions are coming in. I will ask Mauro to maybe read it and he can come online and then tell me that I should answer first this one or not. But
I'm checking and I will interrupt you later.
All right, thank you. I will just check here the slide first. So I give here two different examples. Here we have the same relay. We have here the load is on. That means here the power on the solenoid, on the coil is on. I mean that solenoid is here in this case most likely in an open position. The instrument there to our final element could flow. That means we have to monitor here, of course, the supply of the voltage itself, of the field power supply. We have to monitor that. We also have here the monitoring of the load and the current that we can configure in our smart relay. And here we have the de-energized, or here we have the load is off. So that means we are opening the load, but even on opening the load, here we still have here an earth leaking detection on our smart relays, which can be programmed. Again, this is maybe too much product related, so I don't want to give you a product presentation. I want to give you the main principle of de-energize. I see that Mauro is coming online with the video. Do I have to answer this first, Mauro, or should I first read this?
No, you go ahead and then I will, before to the next.
The next one to de-energize is the simple solenoid. And you can say it's only a solenoid. I mean, it is not rocket science, it's a solenoid. It's on, off, it's open, close. And I fully agree. But as everyone knows, the majority of all the failures in the field, unfortunately, are the simple things, not the complex things. It's typically the cheapest things, typically, are very often also those who will give you some issues on reaching or not reaching your safety function. We have another reason for that. When that solenoid in a normal operation, and assume that your normal runtime of your process or your production is maybe 1 year. Well, if this solenoid is 1 year in the same position, you may have to ask yourself the question, will that solenoid be able to move that position, to leave that position, and able to vent the air, and able to shut down? So solenoids will de-energize the coil, and it will be de-energized by the contact of the safety interposing relay. And the solenoid valve needs to vent the instrument air. Of course, if you are using one single solenoid, you will not have multiple ways to isolate or vent the instrument air. So you need to look for some solutions. And I just wanted to say, I'm not want to propose here that solution, but that's just from a very good friend of mine. That is one of the solutions he had on a huge chemical plant, which will be starting up in Asia a couple of years ago. It was an American multinational. And there are multiple ways to isolate or vent with this type of configuration. On this picture over here, there are two different air pads. You see here 4 independent solenoids. And those 4 independent solenoids are somehow configured with those 2 manifolds in here and with this piping in between. And they are actually somehow configured in a 2 out of 4 D. And the D stands for, that was a bit of a challenge for me to understand, but the D stands for the diagnostics, because there is a PLC in there. And they continuously block and bleed those solenoids. They measure them back with some pressure switches or pressure measurements here on those manifolds. And that system got here at that time a approval for a SIL 3 application. So what I'm trying to tell you is the following. Make sure that if you have this safety loop with your safety valve at the end and you're using one single solenoid, well, this one single solenoid may be causing you for not achieving your safety, and you will have to find somehow multiple solenoid configuration where you can have an air supply and also a air venting integrity. And especially the air venting integrity becomes very important in some of the installations, especially when you speak about the Energize to trip. Right, last but not least, I was a couple of days ago, I was doing a full-blown training virtual for a system, let's say, that was based in South America. And we were discussing redundancies, we were discussing multiple sensors. Very often you will see 2 sensors, 3 sensors in a 1 of 2 or a 2 out of 3. Then they're using here multiple barriers. Of course, they were using redundant safety PLC configuration. Like we see here, a 2 out of 3 picture of one of the system vendors. Here they were using then interposing relays. And that's all redundant, all the way up to here. And then you come into the final elements, and they go from redundant channels, from redundant input, redundant voting, redundant logic, redundant relays, they go to one single final element. Because the thing is, they said the final element cost too much money and we could not install 2 valves. We were only allowed to install 1 valve. So then you can ask yourself the question, what does it make sense for us to build everything redundant all the way up to the final element when I still keep on maintaining a single element at the end of our safety loop? So last but not least, no matter how redundant your fault tolerance may be, when you are down to 1 final element, well, you can already imagine if there's 1 final element is not moving, it didn't make sense to build up all your redundancy all the way up to a single decision maker again. When you have a fail to close valve, the question you have to ask yourself, the question is the following. What in case of an internal failure inside this 1 single valve? Can I close it or can I open it? And many subsystems assemblies, potentially different vendors, because that picture over here may have potentially 3 different vendors supplying you the ball valve, supplying you the actuator, supplying you the positioner. That means very often those subsystem vendors are not working with each other. They are independent supplier of a particular functionality. And then you as an end user, you need to try to figure out how can you get a certain still class on that. And we all know that's a big issue today on the market. The only thing I want to say is the following. There is a new functional safety standard specific for these topics, for the safety related automated industrial valves, is under development. And I can only give you here this reference, that's Technical Committee 69, which is from the Synelec, and there will be a new functional safety standard, that's here the working group, there will be a new functional safety standard being developed specific for this valve. All right, Mauro, we have the next.
Yeah, before this question, before this poll, we have this question which has to do with cable length and voltage drop. So the question is whether the IEC standard deal or define what is the maximum distances between the relay located in the control room and the solenoid, for example, located in the field, taking care about the voltage drop.
Clearly, the voltage drop, as it is an issue in the instrumentation, cannot be handled by the IEC standard. The IEC standard is all there to achieve a safe position. Now, when the voltage drop, simply speaking, would be getting too much under the specification to keep the solenoid open, the solenoid will go to the safe state. So from a safety point of view, a voltage drop is not a problem. From an availability point of view, a voltage drop can be a problem if you have to keep that solenoid open for your production. But the voltage drops itself, such specific details on the 61511 are not described. But I'm pretty sure if you take your vendor specification of that 1 solenoid, which has been used in that loop where you have considered or where you're investigating that voltage drop, you need to reach the specification for the solenoid to maintain it open. So that's something specific, dedicated to the device of the solenoid. But from a generic point of view, from the 61511, the safe state is the one we try to achieve. So when the voltage drop becomes too low, and my solenoid is still, in that case, when the voltage is too low, cannot maintain the coil to be energized, is losing the capacity to keep the coil open or energized, it means then the spring in that solenoid should be able to close the solenoid. So from a safety point of view, a voltage drop would not be an issue, okay? But of course, it would be an issue if you want to look at maintaining your production, because then the voltage drop would be considered in the normal, let's say, engineering words, we would call this a nuisance trip or maybe a spurious trip. And that is something that we want to avoid because our production people would not be happy if we would have this. Right, coming back on the poll, that's the last poll for the webinar. On the second last poll, we have one more at the end. So
okay, let's launch. Shall I launch or do you want to read the question?
You can launch it and I will still read the question at the same time.
Okay, I launched the
so as per the 61511 standard, which hardware concept can be SIL suitable or SIL compatible? Do you think A, only de-energized to trip, means the prevention protection layers are described in the IC 61511 to be suitable to be built as de-energized? Or do you think energized to activate, which I know we call it before energized to trip? I don't like the word trip when we activate, but that's another topic. That's the mitigation layers. Or do you think both A and C are suitable, compatible by the 61511? Or as always in the multiple choice questions, none of the above. Which one do you think is actually being described or suitable to be used by 61511?
Okay, let's just wait a few seconds again and then we end the poll. I will end the poll now and I will share the result. Here it is.
Okay, and again, the majority here, 63%, is saying both de-energized to trip and energized to activate can be used also in the hardware concept from the 61511, and that is 100% correct answer. The very common misunderstanding in the industry, and I know where it comes from, but that is another point. Let's focus on addition two. But the misunderstanding worldwide by many engineers is as 38% here in this group is saying only de-energize is allowed or suitable for SIL. That is not correct. And I'm going to come back on this, especially that is why we have now made, I will stop sharing this, Mauro. Okay.
Yes.
I will just go on the last topic and there you will be explained why this is a misunderstanding. Now, energized to trip, as I said before, I don't like to call it trip. Why not? If you start a pump, if you start a deluge system, how can you call it a trip function? Because you start something. So it's something fundamental in my mind as being an engine nerd, maybe. If I open something, if I start something, like for instance, I'm opening here a deluge valve, or I'm starting a motor, I'm starting the pump of my sprinkler system, how can I call starting a pump on a sprinkler, how can I call this a trip function? So it's purely because it is de-energized to trip, and in the old terms of the standard, we still call it today in the new standard, by the way, we still call it energized to trip. It's only me here, being the engine nerd, saying I will call this energized to activate. So the first thing to realize, energized to activate is never fail-safe. Because fail-safe principle is you remove the power, you have to go to a safe position. As I said before, when you have an internal failure in your system architecture, how will you power on a channel if that channel has maybe a problem? So you can say, yeah, you can have some redundancy, but still, if you think about it, and I will have some other question coming on one of the next slides, a spurious trip on energized to activate is very rare. Any plant you may be working on, or any end user you may be talking or dealing with, ask him how often have they seen that the deluge system spuriously is starting for no reason. But when you ask the same end user, how often have you seen your shutdown system to go to shutdown for no reason, everyone will say, we have seen that. Because that is the fail-safe principle method. You cut the cable, you remove the power, typically you will create a shutdown. But here in this case, energized to activate, if you cut that cable, you will not be able to power on the solenoid because the cable is gone. That means we will have to do something more. And that is where we will start to talk and introduce here about the line and the load monitoring of your devices. So the power itself in this principle, energize to activate, is the availability of your safety function. And of course, it also has a reliability, because again, when we have this under voltage here, or we have the over voltage here, well, again, that will be also a problem for energize to activate. Common examples would be deluge systems, fire and gas systems, fire suppression systems, foam systems, high voltage protection, alarming systems, etc. Since in normal operations the loop has no power, that is where you will find that line and load monitoring on the digital output modules of your safety PLC, and on the same principle on monitoring the output signals of your interposing relays. And again, there are some interposing relays that goes further in diagnostic efficiency, let's say information, and they can feed this back inside your BPCS, DCS, or inside your safety PLC. Things to monitor will be like open circuit, short circuit, loop resistance, leaking, earthing, etc. Again, simply speaking, as I already mentioned before, how do you turn on the power when the power inside the device has an internal failure? So how will you do that? I'm not saying it is rocket science, but you have to think twice before you start to say that your system is an energized to activate. More to the point, how do you mix on all those safety PLC vendors? How do you mix your de-energize to trip DO module together with an energize to activate DO module on the same backplane, on the same I/O bus? How will you do that? How is this done? How is this working? That's something that you need to check, or that you need to discuss with your vendor specialists. How often have you experienced, I just mentioned that, so let's skip this. So a safety PLC digital output module, as I mentioned also before, often has not the capacity or the power, or let's say the specifications to power your output loops. That means you will use somewhere in the middle a interposing or a interface to interface between your digital output module and between the load of your device. The line monitoring functionality, unfortunately, when you are using a digital output module inside your safety PLC, but that line monitoring of that digital output channel is going to an interposing relay. So in effect, your digital output channel monitoring capacity of diagnostics is only up to the coil of the relay, not up to the coil, of course, of your solenoid. That means the last end from the contact of your relay all the way to your solenoid is getting lost if your relay has not the capacity to have some diagnostic efficiency on the output channel. That is where a smart relay with diagnostics to feed this back into your safety platform could be a good way forward. Right, I make here two examples because I'm in talking to some of the, let's say, the specialists inside GMI, which relay do you sell most? We had some, let's say, discussions about what relay applications they see that people are using. It's not uncommon that people will start to inverse signals with those interposing relays and still maintain a de-energize to trip principle in the safety PLC, but make it an energize to activate through an interposing relay. So you need to be careful to look where has this been reversed or inversed, and that's an example that I want to give you over here. I take here one of the smart relays with diagnostics on this side over here. The input is on the right hand side over here between channel 1 and 2, or terminal 1 and 2 I should call it, and here between this terminal 11 and 12 you have here the load to your, let's say in this case, solenoid. And I call this here a direct straightforward in, out, one in, one out. That means energize the input, energize the load, and the energize the load is done here. You can see this configuration. This is shown here in a normally open contact principle. That is one way you can do it. The second way is just the opposite. So the first you look at here, you can see everything the same over here, but they change the context. They go here to normally closed contact. So in principle now, they're going to de-energize with a normal de-energized principle digital output channel / module, but they're going to energize the output at the end through the interposing relay. and they're going to monitor that, and that is being sent back again as information, or could be sent back as an information to your safety PLC platform. So, conclusion, because I also look at my time and I see we are a little bit behind schedule, but as Mauro is his last day of working, I'm pretty sure he's relaxed as he's going on a holiday this afternoon. So, conclusion, a de-energized to trip is the only fail-safe solution. A energized to activate is never fail-safe. So when you are building and you're mixing those type of principles in one safety platform, please think about what is the difference, because one part will be fail-safe, the other part is not fail-safe, unless, of course, you start to do, call it creative engineering in your design towards the final elements with some smart positioners, etc. Sorry, smart relays, not positioners, smart relays, etc. A de-energized to trip is typically easier to design, straightforward for any engineer to understand. When we are discussing, debating, or doing inspections on site, where do we see people are getting confused? When those system integrators, system manufacturers are starting to mix that. They're starting to mix that inside their installations or inside their cabinets or inside their safety loops. That is where often creativity is often not understood later on by the maintenance engineers, or it is very, let's say, creative engineered to a, let's say, almost a complex level that in the future people will struggle to maintain that creativity and to understand it. So frequently told that DET or de-energized to trip does not need reliable power. Well, I hope that I give you a little bit of the feeling why we should try to use that SIL integrity on the power supply also. Of course, that is not correct, as we talked about those diagnostics with the over voltage, under voltage, etc., as per 61508. And last but not least, that one poll question saying that energized to activate is not 61511 related. Well, it has been, let's say, modified in the text in report number 4, which was released in February 2020, so very recent. That was just before the COVID-19 started, but the document was released by the IEC. It states very clearly that 61511 normative requirement part 1 also apply to the protection layers which mitigate the consequences. Now I got 2 more slides left, and I have to give the word to Mauro again. We as GMI can support you with the life cycle support on all those activities from PHRA, LOPA, determination, SRS. We do, of course, also func safety management and assessment. And I made, on the last 2 bullets, I already made some webinars specific on those 2 items. We also do the life cycle support on the 62443, which is the security risk assessment, which is normative required by part 1. And as Mauro was saying, in normal, let's say normal times like last year, I think I have done personally, together with GMI, 18 trainings in total. That was one of the better years. I doubt this year we're gonna even reach 10, because the way it goes forward is like September still doesn't give the green light to do training. We have only 1 training scheduled, and still it is on track. The other ones are all being postponed again. But I do mainly personally the TOV Alignment Func Safety Engineer Competency Review Program. We wanted to launch end of the year also the fundamentals of cybersecurity, but I doubt with this whole COVID, I can see this slipping into 2021. We also do customized in-house training and webinar seminars as the one you are doing now. And of course, we have the most wanted book in the industry. We have 50,000 copies supplied worldwide. And I give the word back to Mauro. I will stop sharing my slides.
Yes, so your slide was mentioning closing, but in fact we are not closing. We still have
yes.
the question and answer, which we collected during the registration. So
I got in the meantime, Mauro, if I'm allowed, I got in the meantime a live question coming in. When is the next TOV FSE certification program available in the UAE, United Arab Emirates? Well, there I would love to say end of September is originally planned, Dubai/Abu Dhabi. We're not sure yet where it would be held, but as the situation is today, I've been advised politely by the people running the GMI office in the Middle East, in the UAE, I've been gently advised to postpone this, so I doubt it will be September, but I still hope, and I really hope that by October, November-ish, we will be able to do our one remaining training in the UAE in 2020. But again, not in my hands. I would love to do it quicker, but we are in the hands of the authorities allowing us, yes or no, to do a training over there. Right, Mauro?
Yes, good. So we have 4 questions. I said that we collected that during registration. So let's start with the first one: how to justify and qualify the Energize to activate design in SIS since it is not fail safe.
Okay. Well, as you have already maybe heard, I don't know if that person who sent that question was listening also on here today on the webinar. Energize to activate, or energize to trip, however you call it, doesn't really matter now, can never be fail safe. However, some mitigation layers typically only work on that principle. In other words, if you go into the fire and gas, the fire suppression system or the deluge systems, etc., there you will have to provide energy enabled to do something. Energy in the sense of you will have to start your deluge pumps, you will have to open that deluge system, you will have to have power available, you'll have to have water available. So sometimes what you will see is enable to, let's say, try to make sure that the system will work when you need it. They will work with some accumulators. Accumulators will be accumulating the energy, enable that they will store that in a kind of a drummer in a device, enable to provide that energy to that final device to open. That's often what we will have to do. And as I said before, and that's the third bullet here, that report number 4 was released very recently. It's February 2020, describes very clearly. It was often misunderstood that an energize to activate / mitigation layer / fire and gas layer does not have to be built reliable under the SIG 1511. And of course, that is not true. That's also why, if you look in the fire and gas sensors, the fire and gas logic solvers, etc., you see more and more SIL compatible devices / systems coming on the market. Because we have more and more attempts that those integrity of those fire and gas loops also must be reliable. But simply speaking, and I give you a small example of the gas sensor application, which I was doing a discussion on some project in Europe. Like the gas mapping of your sensors is also part of the success of your story. That means the mapping of the sensors is most likely more important than the SIL specific of that sensor itself. In other words, if you put a SIL2 sensor in your plant, but the wind is blowing the gas in the wrong direction and the sensor SIL2 compatible cannot sniff it, cannot recognize it, well, your SIL integrity of your device may be very integer and very good to work, but it cannot work as the wind is blowing in the wrong direction. That means fire mapping and your gas sensing mapping is also part of the success of your story. Yes, Mauro.
Next, here I am, or at least here I'm trying. Here it is. So the next question is, what role does field diagnostic play in fire, gas, and ESD devices, whether it is mandatory, and if there is a failure in a field diagnostic, failure of short circuit or open circuit, is treated as a dangerous failure or undetected or detected?
Yeah, actually, it was a long question, which I was trying to
Yes.
answer, but you can go to the next slide, Mauro, for me. Thank you. I mean, the question itself is very, not say bombastic. It came from a system manufacturer. It's a company which I also know. It came from a specific system manufacturer. So I try to answer first more neutral, and then I go a little bit more details. But the first bullet here, diagnostic information, of course, is a good thing to have. What is diagnostic information? Diagnostics, as we already mentioned there, diagnosing the load or diagnosing the line in Energize to activate is a good thing to have. But even so, diagnostics is also a good thing to have, for instance, inside a de-energized to trip system. If you think about it, if you look at your smart and hard transmitters, you have your NE43 jumper setting from Namur with your upper range and lower range. That's based on diagnostic capacity inside that device. And that is a good thing to have. Like 40 years ago, in 1980, for instance, there was no smart and hard transmitter available. There was no jumper setting available in the transmitter. That means we had to be in the PLC side. We had to be creative ourselves as an engineer, and we had to actually start to program all those diagnostic capacity, let's say, efficiencies. We had to program it inside our PLCs. But now that, let's say, efficiency, that diagnostic capacity has been moved inside the device individually. And I would say, regardless, irrelevant, if it is now for an ESD or a fire and gas system, I would love to have everything as maximum diagnosed. Why? It will help me with the health status of that device. That's the first good sentence that I can give you. Diagnostics is a very good thing to have. It's not mandatory unless that device is being designed by 61508 and they want to achieve a certain, let's say, SIL integrity. And for a certain SIL integrity, they will have to build up a quantity of a diagnostic coverage. And diagnostic coverage, without to go into much in details, on the 61508 has been classified in 3 classes, up to 60%, between 60 to 90%, and more than 99%. And especially, it's those tables in the standards, which are the measurements to avoid and control the failures for diagnostic coverage. You cannot just say we have 99% coverage on our system, just like that. You have to prove to the inspectors based on 61508 that you can actually detect and actually go back to a safe position on that specific functionality for that device as per the standard requirements. And that's what I want to leave it in details on diagnostic coverage. Now, failure will also be, of course, or the information will be, of course, depending on the type of devices, type of applications. It's very difficult to give you one generic answer on your question, will your short circuit be a danger or a safe failure? But I thought, let's just assume that your question is about the short circuit detection on the final element side. That means on the output side, towards your solenoid. And you only have a one-to-one configuration. Well, you can already imagine that potentially when you have a dangerous detectable failure, we call this a DD, the diagnostics will flag this and you have to ask the question, can I still go to a safe position with this failure, yes or no? Now, there is no diagnostic coverage typically on a final element. Diagnostic coverage stops somewhere on the digital output module of your safety PLC, or if you are lucky and you are selecting a smart relay that can do this for you, it can stop over there. But once you are in the solenoid domain, I mean, the solenoid itself typically has no much diagnostic potential unless, of course, you use one of these 2 out of 4 solenoid principles, which I showed you in the Energize to trip application. Yes, Maro.
Yeah, time is running and we are a little bit late, but we have only last 2 questions. If I'm able to move to the right one. Okay, here. I think you answered already during the webinar to this question. So the question is whether Energize to trip loop comes under the umbrella of 61508 and 511. If not, why?
Okay. Well, the design of reliable devices, as already mentioned, must be done as per 61508, which are applicable, of course, for both the Energize and Energize to activate. There's no difference. But the 61508 makes no difference in how to build those devices reliable. That's the first thing. Second bullet, as Mauro said, as we answered before, we can actually nearly skip it, but very briefly, clearly the 61511, the misunderstanding was edition 1 only handles de-energized to trip, which was true. Okay, so the energized to activate was almost like the forgotten item or the odd baby in that standard, because the mitigation layers were almost outside of the scope of the 61511 by edition 1. Now, edition 2 is clearly making a statement, be careful, mitigation layers must be built reliable, therefore also please use the 61511. Yes, Maro, that's probably the last one.
So last question is on power supply. So there is an interest in understanding the choice of power supplies for safety system and interest in knowing how the power supply can affect the sea level.
That actually came from 2 different persons. So I found it interesting that 2 different persons who resisted from 2 different companies, 2 different countries, had the same kind of a question. Although we already handled it before, I made this one last slide here for you. The power supply itself, the power supply actually, it doesn't supply power, it converts power. That means when you don't feed power in, there is no power coming out. It's not self-containing. So Some people said, Tino, it's not a power supply, it's a power converter. Now, listen, for all the instrument engineers out there, all the maintenance engineers, they'll call this for the rest of their life a power supply. So for the sake of simplicity, let's call this a power supply. Okay, so you supply the power to the field, and the first thing that you will look at is always the availability. So clearly, if you use one single power supply and the power supply has a failure, well, it will stop supplying. It's clear. That means we will have to go to kind of redundancy, could be like a 19-inch rack in this case, where you will have, or a certain, I don't know if it's a 19-inch, I don't think so, but it doesn't matter. It's a rack mountable power unit here, and that power unit can be mounted in several configurations that you can create some redundancy, some load sharing, etc., etc. Plus also it can be hot swappable. And of course, as GMI is in the intrinsically safe or in the ATEX world, this one is also for a zone 2, and it will have a SIL 2, if I remember well, or even SIL 3. I need to ask to Mauro because I'm not a product specialist on this, but it has also a SIL integrity, but it is also hot swappable even in your zone classification, which is one of the unique items in here. And what made it now SIL suitable power supply, it's what we discussed already before. It's this part 2 of the 61508 that looks at the accuracy, looks at the under voltage, the over voltage, latch up, inrush current, over current, all that must be monitored. And if that monitoring principle is fulfilling the diagnostic coverage as per the 61508 part 2, which is the hardware part, that what's make this power supply a SIL suitable power supply, where another power supply not having this diagnostic definitions and also capacity as we discussed over here will not have the same SIL integrity. And that's also why those power supplies or suitable power supplies will have a certain SIL integrity and are becoming more and more a common practice. So to answer that one question, will there be an effect on your SIL integrity? Well, SIL, let's make it simple. A SIL is a prediction on the availability of your safety function, meaning that a SIL number will predict what is the performance that this safety loop may have, or what is the likelihood the safety loop will not be able to go to safe position when I need it. As we discussed in this webinar, your safety is also depending on the availability and the reliability of that power supply. Therefore, clearly, it is a good and common practice to think about the SIL integrity of your power supply and not just take a conventional power supply for not having the same problem as they had in Norway on this offshore platform, where there they had a huge incident based on the power supply on a safety loop not doing what it was supposed to do. Right, Mauro, I will leave it like this.
Yes, just to complete the information you gave, power supply from GMI are SIL 3 suitable for de-energized to trip application and suitable for SIL 2 application where energized to activate is necessary. Just to complete.
Okay, thank you.
So, one of the last page of the presentation, just to remind you that after this webinar, we will take some few weeks, 2 weeks holiday, but then we will restart. We have already planned webinar for August and of course September. Most probably we will go even after. So just have a look to our website where you can check whether there is some topic which is of interest for you. And then as Tino was mentioning before, we have our YouTube channel where we have stored all the recorded version of the previous webinar, including this one. You will receive the PDF format of the presentation, and hopefully we will see you again in some other webinar in the next future. We have a very last question for you. Let me launch it. We would like to have your feedback. Finally, I will be allowed to go on holiday just only if we receive the proper answer to this question. So I rely on you. And just, it looks like...
Yeah, and just for your information, I'm only getting paid when I'm not getting any poor. So if there's one in poor in here, then I may have a trouble. No, I'm just joking.
Okay, so I think we can end this polling. We have collected, I would say, very, very good feedback. Thank you very much for that. And as said, we look forward to see you to the next webinars. And hopefully also you will have some rest time. So enjoy that. And let's see in September if situation will improve and we will start having a face-to-face meeting, hopefully. Let me check, stop sharing. Now it's real close, and you have this very last picture. You can see our contact if you have anything that you would like to discuss deeper. If we are also able and in the position to plan some dedicated webinar to dedicated companies if you wish. So you just drop us an email and we will do our best to arrange that. Having said this, thank you very much to all, and look forward meeting you again, whether in a webinar or in person. Thank you and bye.
Thank you, Mauro. Have a good holiday. And thank you everyone for watching today. We will be back later on, as Mauro is saying. Thank you.